Chapter 9, Simulation. So in this chapter, we will discuss the typical polymer flooding simulation workflows, some of the tools, approaches, and limitations. I will also try to give you some tips to navigate this very complex topic, especially when it comes to polymer injection. But first, a reminder, even to myself, I'm a geologist, and I sometimes forget that all models of the subsurface are wrong, but some can be useful. And the reason is we will never have enough hard data at hand to build something accurate. It will remain a black box. And Richard Baker, in his course on water flood and saga, was saying that we sample just 1/10 billion of the reservoir. So what I would say is, so in the best case, your model is inaccurate. In the worst case, it's just wrong. So the question is, what can we do with that? Even for water flood, but let's see what we can do also with polymer injection. Something we lose, and that's for geologists, not to blame reservoir engineers, but something we lose is heterogeneity. So it's one of the biggest problems also why we under-design, I would say, the injected viscosity, is because the coarse models we often have mean that one cell might be 100 by 100 meters or even 25 by 25, which is not bad, but imagine 100 by 100. For a geologist, it's a nightmare. So there is no surprise that when you start polymer injection, you will miss a lot of things. You might see early breakthrough or late breakthrough. I mean, nothing will work as expected. So in our case, what we are missing is we are losing heterogeneity when we just upscale. And then we pay the price when we start injecting, especially our polymer, because we see things that no one would have ever expected. So what are the stages of EOR simulation? It's like for probably everything else, which means you start with the geological reservoir characterization, you build your static model. Then if you have history, you try to match the history of the field. It's always interesting to see that people like to explain the past and not try to predict the future. So we'll come back to this in the simulation of polymer injection. Then you can history match the core. Why not also try to predict the pressure drop in the core to see if your mathematics are going well? But we'll discuss this also a bit after. And then you go to forecasting and sensitivity analysis. So you can do it in 1D, 2D, 3D. Of course, most companies, given the complexity of reservoirs, like to use 3D. But sometimes a good Buckley-Leverett can help you benchmark your results with the expectations and compare the patterns. So for polymer flooding, we need to ask ourselves the right questions from the start. Do you know your reservoir? I mean, that's key because this will tell you where to inject polymer, how much oil is left, where. Do you have sieve zones? What is your sweep efficiency? What viscosity do you need to inject? So, and other questions. So the thing is, do you know your reservoir? And yes, the answer is, if there is no answer, maybe you need to find new approaches, new tool, AI, whatever, to help you, sort out the wheat from the chaff and say, okay, now I think I get a clearer picture and I can start putting money on the table to do my project. Are you sure about the mathematics behind the software used? These are black box, and like the reservoir, by the way. And so the thing is, for polymer, do you understand the equations? So first, do you understand the polymer? Do you understand the rheology? And do you understand the equations people are giving or using in the simulators? And do they mean anything? So of course, it's difficult to take the time to learn, but it's much harder to take the time to fix wrong predictions, sometimes really wrong predictions. So the idea is just at least to go and dig into the manuals and understand what people are using and if it makes sense to you and for your needs. Do you understand everything about polymer solutions? So it's linked to the previous question. If you don't know anything, you won't be able to understand what people are using in the simulation. The next step will be reservoir simulation for EORs. So what we want to do is really want to build the business case. But you will see that, most interestingly, the most important parameters that we need to build the business case can't be estimated in the lab and are wrong with the simulation when it comes to polymer injection, namely injectivity and or recovery. So if you can get injectivity right, and we'll come back to that, how can you predict anything else? And the 3D commercial simulators, so far, my experience, all of them, have been notably wrong at predicting injectivity. So what kind of use do you have with something that cannot give you the most important value to build your business case? So in the OR world, you have several companies, several suppliers. So we have some of the names here. And once again, today, from my experience, none or very few exceptions, so none of them have been able to predict correctly injectivity during a polymer flood. So what can you do with a model that is not able to tell you the most important parameter? So that I think personally there is some work to be done to change the approach and the way polymer is modeled. And I'm, again, happy to start discussions. What are the main unknowns? I believe there are too many keywords for polymer. So keywords are fine, but you need to understand when to apply them, and especially if, because you have seen something in the lab, it will translate in the field. Let's take shear thickening, for instance. Yes, you will likely see shear thickening in the lab, but will it even occur in the field? So if the answer is yes, please tick the box. Personally, I'll try to avoid even having shear thickening in the field. So I don't have to study it in the lab, and I don't have to tick the key box or the box in the simulator. The use on non-Newtonian behavior can be tricky. What you need is Newtonian plateau, so the viscosity at low shear deep inside the reservoir, and some maybe shear thinning in the near wellbore area, depending on your rate and well configurations. That's probably it. Of course, we, I think, poorly understand and model the near wellbore area. It's clearly a place where everything is happening. If you have induced fractures, skin, you have eye shear, then it goes back leaking in the matrix. So that's really a key place where you need to have a much, I would say, smaller grid, so smaller blocks, to really capture dynamically all the changes which are happening at the wellbore, including induced fracturing, because even induced fractures might likely extend over the duration of the project. You don't capture fracture formation, that's exactly what I say. So some people try, some others do, but not everyone, not for every project. So it's something you need to assess in the field first. Do you have and will you have? And if the answer is yes, you need to put them in your simulation. Maybe not using negative skin, it's a bit cheating, but to find a way to really make something dynamic, moving and changing over time. So there is also the big problem of modeling viscous fingering. If you put in a simulator a residual resistance factor above 1, it's likely that when you will go to water injection, you will see that the water will push the slug, be diverted to other zones, and you will get extra oil during water chase. The field cases I've shown and the principles we've discussed show that it will likely not happen. So if it does happen, it means you are certain about the measurements you made in the field and what will happen in your reservoir. But all the cases I've presented show the exact opposite, which is that when you resume water injection, it's over. There is a huge impact on the design strategy, obviously, because if you want to run the economics, you need to know how much you inject. But if you can't predict how much you will inject, how can you run your economics? That's why very often it's good to go to the field first, a pilot, injectivity test, and then to go back to the simulation, understand what should be tuned to get these values, history match, how we call it, and then try to understand how you build your business case with real reservoir data. You of course need to benchmark with the literature. If you start simulation and your simulator is telling you that 1 minute after starting polymer injection, you have already reached your BHP constraint, it's wrong. No one has ever seen that. So please go read some extra papers and try to understand what's wrong with the simulation. There is, of course, the upscaling issues from the lab to the field, especially oil recovery and some other parameters. So that's really are some of the key problems I would say you need to address before you say, okay, I trust my simulation. What are the warnings? So once again, the understanding is key, reservoir characterization, because heterogeneities will be the biggest challenge you will face, the problem you will have, if you don't understand where are the paths of least resistance, where are the water fingers, and basically it will not help you design the right viscosity. Once again, the results are only good as the data you provide. We all say garbage in, garbage out. The same for polymer, even worse given the physics in place. And when you talk about model calibration, you might need data, that's for sure, but be careful on which data you use and how they have been obtained. So the most important data we will see are resistance factor versus velocity and retention. The rest, honestly, can be discussed. And never ignore field data observation. Spend some time reading the results of other people, not the simulation results, actual field data, especially injectivity or recovery and reservoir responses. How to model polymer injection. So what parameters are required? I mentioned resistance factor, velocity, and retention. And the question is, when you don't understand how you can model injectivity, the best would be to have the right equations. So we know that Pieceman model, for instance, doesn't work. Maybe the equations have to be changed. Maybe you have to have dynamic induced fracturing, maybe negative skin. So whichever approach fits best, but the idea is it might be the first place you have to look if the injectivity prediction is wrong, is the near wellbore area. That's probably the key. What are the constraints? So max bottom hole pressure and max rate. So this will obviously condition your results, especially depending on the inputs and the mathematics used to model polymer. What are the additional parameters which are not taken into account? Very often drag reduction is one. We mentioned that, which means that in the well, if you don't have a pressure gauge, you can't measure the exact bottom hole pressure. And so the simulator will start with the wrong pressure. So very often the pressure at the beginning of polymer injection, bottom hole, is lower than the injection pressure during water injection, just because of the drag reduction effect. So what are some tips? Maybe you can start with something very easy, benchmarking with 1D Berkeley Leverett. There are some analytical tools. I'll show you also a very old model called the PFPM. That's not available on the internet anymore, except on my website. Then you have field model, history matching, and the rest. And so every time people try to run simulation and go to the field, if you can, just because you will need the injectivity eventually, try to go to the field first, get the injectivity, and then go to start your model. So once again, summary, you need to understand the reservoir, you need to be sure that you understand what has happened before, design the right lab test, and then go for your simulation. So you can start with fractional flow. So fractional flow works very well. I mean, obviously. The thing is, some people and operators like Hillcorp have been using fractional flow to benchmark the recovery, and they have very good insights about what's happening. And fractional flow also tells that you should consider increasing the viscosity of the injected fluid if you want to improve the recovery. So basically, you should not do water flood alone, you should do viscous water flood from day one. That's what's coming from fractional flow. So there are some people who assess this with fractional flow. You see the recovery. So the maximum here is 17%. And so they have 17% recovery factor in some cases, some patterns, which is matching their fractional flow expectations. So that's a very good start. Honestly, you can start with basic fractional flow. The mini point example I was just mentioning, you see that you have the fractional flow calculation showing the great benefits of implementing polymer injection in secondary mode. So that's a very nice example that you can use, very basic tools, to benchmark all the results. Then there is another model that's called the PFPM, so Polymer Flooding Predictive Model. I think it was released in 1986, and it's not available, I believe, on the internet. I have it on my computer somewhere. And so it's a stream tube model using also buckley leverage, a bit more complex. You can have up to 8 layers. You can input resistance factor, retention, and the rest. So there are a few constraints which are very well designed. And you can get amazing examples calculating the oil peak recovery with water flood, polymer flood after water flood, polymer flood without water flood. So you can really input a lot of things, and you can calculate the OPEX, you can see the recovery, you can compute mobility ratios and all the economics. So you can really even put the equipment cost, etc., even the tax, etc. So it's a very comprehensive, quite simple, a bit more complex than standard buckley leverage because you have 8 layers max, and very honestly, very, I would say, not accurate because the geology is not captured, but it's a very good tool to build a baseline for your simulation, to understand what you can get out of the pattern or the reservoir you are considering. What's used now in the 3D simulators? So you have very often viscosity versus concentration, retention, degradation, some keywords to model polymer degradation. The thing is, all these things are representative of the field and the core. So in most cases, the answer is not sure. For instance, if you input rheology curves, we've seen in the chapters about the lab test and polymer selection, that two polymers giving the exact same rheology curves could have very different resistance factors in the core. So how do you do when it's like that? The best option would be to find a way to use in situ rheology curves, which are resistance factor versus shear. So I don't know anyone who's doing that right now. I might be wrong. There are some simulators where you can include resistance factors, that's for sure. So it does exist. The question is who is doing that? Most people are using inputs from the lab rheology curves, which once again are not very accurate because you have no impact on retention, permeability, polymer relaxation time, and the rest. So it's very inaccurate. So starting from this point, I still don't expect to have very good injectivity predictions or recovery predictions if the first inputs are deviating from what we see or what we should see in the core. So the first one, as mentioned, is viscosity resistance factors. So if you use something from the lab andriometer, you are missing the point. You don't have the permeability effect. You might have some shear effect. And also, oppositely, in the core, you might consider shear thickening. That's something which is not existing in the field. So in both cases, you really have to understand what you are looking at, what you need, and if the data you have in the lab is representative of what you have in the field. If not, you have to find a way to tweak that or to ask your software provider to change the module or the equations to say, look, here's what I want. Can you make that for me? And so, for instance, the fact that the in-situ resistance factor will change with temperature makes it even more difficult. So I'm just talking about some exotic polymers here, but that's the exception. That's proving my point about not using rheological curves, is because some polymers will have very different behaviors in porous medium. And with one polymer or two polymers which have the same curves, you might have very different in situ behaviors. So the methodologies for dynamic modeling is answering the question also for polymer, why is injectivity often much better than expected? It's something I discussed in the injectivity chapter, is basically because of the expectations. And the expectations are coming from the models. So I know people who never tried in the field to inject polymer, just because the simulation told them that it would never work and that they would never be able to inject 2 or 5 centipoise, despite all the evidence from all the projects that no one ever had any problem. Trusting the simulation too much can stop you from recovering some extra oil when it comes to some EOR techniques. So here you have an example where the impact of the grid size, of the accuracy, if you want, of modeling the polymer injection. So that's something which is key here. That's one of the problems. There are many others. I mean, challenges, I won't say problems, but you have to be aware of that when you start modeling polymer injection. And so I mentioned the need to refine the grid. It's especially true in the near wellbore area. If you have induced fractures, if you have skin, that's where basically there is the shear, that's where the shear is changing the fastest. The near wellbore area is a place where you go from very high shear, especially in vertical wells, to very low shear. In horizontal is different, might just be low shear. But in most cases, when you have vertical wells, it's the place where everything happens, fracturing, shear changes, and the polymer going inside the matrix. That's a place you really need to focus and to understand what's happening. And so, interestingly, you will see more and more publication using analytical tools, again. So it's recent. When you look at the dates in the papers, it's 2021, 2, 3, 4. And so people are coming back to analytical tools just because they have not been able to predict the injectivity with 3D simulators. And once again, if you can't get the most important parameter right, how can you even build your business case? So a couple of references here to have a look. And so the idea is to use equations characterizing the polymer solution versus shear. So near wellbore area will be very likely high shear, and then you will go to out to the deeper reservoir where you have a decreased shear. So the first one will be inside the wellbore, and the further away you go, basically, you will adapt the equations to mimic the rheological changes of the polymer solution. So it's something that is being used more and more to try to predict the injectivity, because the other approaches don't work. Another thing also is the upscaling. We mentioned that. So it's obviously way more complex in the reservoir. So you need to take some inputs from the core, and then the upscaling issue is an everlasting question, I would say. So something can be upscaled properly. Imagine that you get resistance factor in the core, in a permeability. We could say that in theory, every cell which has the same permeability and same characteristics should see the same pressure drop profile, at least in terms of pressure drop. Then depends on oil saturation, but for retention and the way polymer is saturating the rock, you should have something which, if you can do it in the lab in 1-Darcy and pushing oil, or just at SOR, you can say, okay, normally in the field, in the same rock type, I have something like that. The question is, how many then rock types do you need to characterize to be confident that what you will obtain matches the actual field result? So you will lose heterogeneity. It's the biggest problem because it will impact how much polymer you will inject. And because this will be also something probably that the simulation will tell you, which is if you want to get 10% oil, the maximum viscosity you need is 10 centipoise. Because at 20 centipoise, you will recover less oil, which doesn't make any sense. But when you start looking, the reason is because at 20 centipoise, the injectivity is decreasing so much in the simulation that the mass balance makes you don't produce any oil. But again, is it true in the field? Like, will I see injectivity decrease if I go from 10 to 20 centipoise? Maybe not. So once again, it's a very critical point to bear in mind. So of course you can do sensitivity studies, but for this you need to get everything straight in the first place. If you don't have characterized heterogeneities, how can you run sensitivity on viscosity? At some point it will make no difference. But when you start in the field, you might see early polymer breakthrough, and you have to go back to the model because there was a sieve zone here and no one saw it. So I lost something there. Another example, you see the impact of the grid size on the results. That's obvious. It's especially more obvious for polymer, especially where shear is changing, which is a near wellbore area. But it's the same for heterogeneities. So the idea is you might have to play on grid size, at least, especially in the near wellbore, to capture the phenomenon and understand what's happening with the injectivity. There is the issue of modeling viscous fingers, which is very difficult. There's been a lot of papers, publications. There will be still some challenges linked first to the accuracy of the geological model and the grid size, and then some other numerical effects. But the idea is, well, if you can't properly capture viscous fingering, be careful, for instance, when you model water chase after polymer injection. It might give you a very optimistic but wrong results, saying that the polymer has damaged the rock, there will be no fingering in the hyperm zones, water will be diverted, and you will get 1% extra oil just during the water chase. Once again, so far, field evidence has not corroborated that. So what could be some modeling tips? First one, if you can, is to use not rheological curves, but in situ rheology, including resistance factors versus velocity and retention. What you can do is to try to take two rock types, which are the extremum representing a reservoir, so the highest permeability and the lowest permeability, which are representative still of the, I would say, the majority of the rock types. And you run polymer injection in both, and you take these values, retention, resistance factors, and maybe residual resistance factors in low perm rocks to take in your simulation. The velocities you will be studying in the lab, you need to take them from the field, especially what's going to be the velocity and shear rate deep inside the reservoir. And in most cases, you need to assume a residual resistance factor of 1. Because once again, the water will likely break through the polymer. So if you put something more than 1, it means you have measured it properly in the lab, preferentially in low perm rocks, and then you can use it in your simulation. So after a field test program, you need to refine the grid and understand the near wellbore. If you can, before running the simulation, run an injectivity test to get the values and compare with simulation. So that's going to be very, very important. You need to run two cases. Very often people start with a bottom hole pressure constraint because they are afraid of fracturing, even though very often they already have induced fractures. So if you start with BHP, given the way polymer is modeled and the mathematics used today, it's very likely that you will see a very fast pressure increase. So you will reach the BHP very fast, then the simulator will automatically decrease the rate, and your project is becoming a failure. So what you can do is to do the opposite, which is you put a fixed rate and you remove the BHP. It will likely be much more closer to the truth than the other case. And so the truth will be in between the BHP constraint and the no BHP constraint. So that's going to be something you need to run, is to run both cases, and the truth will be somewhere in between. You once again need to input RRF, or residual resistance factor, above still equal to 1, above 300 mRC. Below, you have to measure it. Just don't put any value because you read a value in papers, you have to measure it. It will have an impact on your simulation result. And of course, if you want to assess the displacement efficiency of polymer by water, remember all the principles we've discussed in this course, the fact that there is a viscosity difference between the polymer and the water, that the water will likely not push the polymer, but likely break through it. And so that if you have a lot of incremental during the water chase, there is likely a problem. Some other tips. So to model viscous fingering, well, you also need to be very accurate geologically. You need, again, to evaluate the results based on reservoir engineering principles. Once again, if the simulation tells you that you recover more oil by injecting 10 centipoise instead of 20 centipoise, there is likely a problem, and the problem is likely that you have a bottom hole pressure constraint. And the injectivity is being decreased just because the rate is being decreased. Once again, I would prefer that you try this during the pilot to test the reservoir limits, because from experience, no one has ever seen recovering less oil by injecting 20 instead of 10. It would be the opposite. Just because the reservoir is heterogeneous, and so 20 will sweep more than 10. So that's the basics. If the simulator predicts 50% loss of injectivity right away, was it ever observed? In which cases have you seen 50% loss in injectivity the minute you switch from water to polymer injection? So if no field case is corroborating this, then there is a problem. And of course, there will be still a need to understand what will happen in the long term in the wellbore area, especially in these fractures, if, for instance, you have vertical wells. What kind of sensitivity analysis do you need to run? It will be mainly on resistance factor at fixed rate that you will get after the pilot, retention and stock size. We know the results. I mean, the higher the resistance factor, to some extent, the higher the recovery. The higher the retention, the lower the recovery, and the smaller the slug size, the lower the recovery, given all the principles we have discussed in the slide. So by running sensitivity analysis, it will be more to find the balance between the economics and the results, assuming that you have your model right and your equations and inputs right, which is probably today the two keys: heterogeneity, so the model, the grid size and what it contains, and the polymer features. So polymer are secondary now. This is something we've seen with ILCorp. There is no notion of incremental. You are just pushing oil, fresh oil. So the idea is that the trend will be similar to water flood, just much longer oil production plateaus, sometimes with even higher production values, and of course, lower water cuts. Some additional thoughts. So of course, we mentioned fractional flow. It's simple, it's a guide, but it's very good for benchmarking. You can't do everything. You can use simulation, garbage in, garbage out, understand the polymer features, understand the polymer keywords, read the manual, what people are using, does it make sense, and benchmark with results. This is the second one, so anticipating, you need to confirm that with field cases, as for instance, anyone seen a dramatic injectivity decrease. I see one in my simulation, as anyone else observed that in the field. In the simulation, everyone is seeing that, but in the field, has anyone observed that? If the answer is no, then it's likely that you have to find out why. And in my experience, and I'm not the only one, obtaining nonsense answers from simulation is the norm, not the exception. So of course, the question would be, why do we keep using them if we can't get the value straight? Again, it's not black and white. There are things that can be clearly improved. First, geological understanding. Second, the way we evaluate, the polymer flooding parameters in the lab and which one we are using in the simulation. And the reason is, again, assumptions. So which assumptions do you have? You put BHP constraints, but maybe you already have induced fractures. We have seen this in the reservoir response chapter. Some people put the fracture pressure very high, and the pressure during injection was lower, but not changing when they were going from 50 to 100 centipoise. So maybe the frac pressure was wrong. So once again, be confident about your data, go back and check, do some extra tests, because this will be really key to get your injectivity, economics, and business case right. Extra thought. So the right resistance factor, that's the conclusion. Viscosity is different than porous media. Of course, you need some good real perm values, especially in heavy oil, to get the right injected viscosity. My opinion is that if the software is asking for a viscosity curve is wrong for the reasons I explained, which is two polymers can have the same viscosity curves. They might have very different in-situ resistance factors. So this you can't guess. You have to take the data you have in the core flood, for which you are probably already paying a fortune. So instead of history matching the core flood, it would be good to try to predict what would be the pressure drop in the core flood with the inputs you have from Polymer. So you try to model the core flood, you simulate Polymer injection in the core flood, and then you start by comparing the results of the core flood simulation to the actual core flood instead of history matching. And if you see large differences between the simulation and the results, there is no need to go and upscale anything. Something is wrong in the first place. So you have to understand already what's happening there. And of course, how the RF in the lab and the field compare, something we have discussed in the lab test. About retention, so something critical about retention, it will be likely underestimated in the lab because we have lost heterogeneity in the core. So in the simulation, also what we have to understand is depending on retention, if you inject a concentration that's too low, you will likely fail because you will lose polymer that will not displace the oil bank. And so in the simulation also, if you are adding other chemicals, such as sacrificial agent, be sure that based on the difference in viscosities between the agents and the polymer, that they are contacting the same pore volumes. They only need to consider sacrificial agents to help, for instance, the economics in the field and simulation. Would be if they have the same, they are sweeping the same areas together. If there's a difference in viscosities, it won't be the case. And so some shear something effect in the simulation is, yes, shear thinning you might have in the well bore, depending on the shear rate. Maybe less in horizontal wells, very likely in vertical wells. Shear thickening we discussed already. Shear thickening is a lab observation in a core, one-way flow, high velocity, no fractures. If in the field you have induced fractures, even perforation or anything, it's likely that there will be no shear thickening because there will be no matrix. So the moment you enter the matrix, the shear rate will already be much lower and it's likely that you will not see this effect. And what I said several times is it's better to avoid shear thickening in the field by doing everything right, and also in that case not to study it in the lab so you can avoid even ticking the box in the simulation. And so for that you have to design the right injection completion wells and look at the injection strategies. And residual resistance factor, I mentioned that. Please, you can use it in the simulation, but you have to measure it and understand the consequences of using a value above 1, which is damages, which is that the water in the simulation will not finger through the slug as fast as it would likely do in the field, assuming that, of course, you have heterogeneities and you have designed everything properly. So if you do input a value in your simulation, you have to measure it and you have to understand what are the consequences of putting this value. So the slug will not be pushed, the water cut will increase rapidly once water breaks through the polymer slug. And so it's not even mentioning that the value you might be getting from the lab and input in your simulation might vary depending on the procedure, how many pore volumes of water have been injected to calculate the value, etc. So it's complex already. So it's adding more complexity when you try to tweak slightly these input parameters. So what are the conclusions? So I believe, maybe these conclusions for these topics, but that today commercial simulators are using some keywords which are either not correct or not properly used. So properly used is not the fault of the simulation, it's the fault of the user who doesn't understand what he's doing. But some example, personally, I would not use or input viscosity curves. I would put in situ viscosity curves, so in situ rheology. It's the same, the difference is not viscosity concentration, it's viscosity shear, but you can have different curves at different concentrations too in the core. It's easy to run. Then shear thickening, shear thinning, you need to be careful when and how you use them. You have to find a way, instead of studying polymer degradation, to minimize it. You can input something in simulation just for assessing variability. But in the end, if you have a problem, if you have so many parameters, how do you know which one you will change? Will it be retention, RF, RRF, clay lithology, polymer adsorption? So we don't really know. Salinity, mixing parameters, the gamma factor, these kind of things, we don't know. So my point is, it would be much easier to take few parameters who make physical sense and to use them. Injectivity in simulation is always very pessimistic, always, for a variety of reasons. The thing is, we poorly understand the near wellbore, and sometimes the user poorly understand the physics and the polymer. So if you see poor simulation results regarding injectivity, go and check the literature and see if anyone has ever seen that. Data disappear with upscaling, including the possibility to model viscous fingers. Other reasons too, but that's a big one. Near wellbore effect and fractures, you have to take them into account. You have to model the induced fracturing. It's likely you have. If you don't, it's likely you will lose a lot of injectivity. But if you start and you don't lose injectivity, it means you had fractures. And the water chase is often not properly modeled, so there are a lot of papers, publications, and attempts. It's really going in a very interesting direction, but there will be still some challenges linked to the accuracy of the geological model. And so maybe the conclusion for this one, and I will probably not be making many friends, is are these 3D simulation models for polymer useful if they can't even predict injectivity, which is the most important parameter to build any business case. So with that, of course, there's some work to do, and really hoping that there will be some discussions with all the peers to try to really improve that. Because again, today, more and more people are coming back to analytical tools to try to predict polymer injectivity. Because I repeat myself, but if you don't get this right, there is no business case.